Good afternoon, everyone, and welcome to the last session of the day. We have two speakers. One is Dhananjaya Sahu and Sampath Kannappan, my old friend. So, Dhananjaya is from IMSC. I don't think I have to introduce you here. He will be speaking on an extension of a theorem of Heilbronn. So, you have 20 minutes from now.
Thank you, sir, for the introduction. And I would like to thank the organizers for giving this opportunity. Today we'll be talking about extension of a theorem of Heilbronn. Isn't it working? It's working. It tells about real zeros of Dedekind zeta function. So I'll start by defining Dedekind zeta function. So let K be a number field. For complex number S with real of S greater than 1, the Dedekind zeta function zeta k of S is defined as summation over non-zero ideals of OK 1 over index of I in OK to the power S. It has anti-continuation to whole complex plane except for a simple pole at S equal to 1, and it satisfies this functional equation zeta k of 1 minus S is equal to AK of S times zeta k of S, where AK of S is dk mod to the power S minus half cos pi by 2 S to the power R1 plus R2 sin pi by 2S to the power R2 2 times 2 pi to the power minus S gamma of S to the power n, where dk is the discriminant of k, R1 is number of real places of k, and R2 is number of complex places, and n is the degree of the number field. We know that zeta k of S is non-zero for real of S greater than equal to 1. So from the functional equation, we can say that zeta k of minus 2n equal to 0 for n belongs to natural number. And when if k is not totally real, that means if R2 is not equal to 0, then zeta k of minus n equal to 0 for n belongs to n. These are called trivial zeros of Dedekind zeta function, and zeros lying inside the critical strip are called non-trivial zeros. This is the critical strip. This is 0, this is 1, this is half. And the generalized Riemann hypothesis predicts that all the non-trivial zeros of zeta k lie on the line real of S equal to half. So if we are looking for a real zero, the first guess would be half. We know that the Riemann zeta function, it doesn't have any non-trivial real zero. So we can ask, does there exist a number field? K such that zeta k of half is 0. Hermitage answered this question. In 1972, he showed that there exists a number field k such that zeta k of half is 0. So we know that there exists a number field k such that zeta k of half is 0. So do we know something about order of zeta k at half? So from the functional equation, we can say that half is an even order 0 of zeta k. I'll give a quick proof of that. Let m denote the order of half. Suppose m is odd. We know that zeta k satisfies this functional equation, zeta k of 1 minus s equal to ak of s times zeta k of s. Ak is defined there. Now we'll take the mth order derivative of this equation. So since m is odd, we'll have minus zeta k, mth order derivative of zeta k, 1 minus s. This is equal to mth order derivative of zeta k s ak of s plus some constant times m minus 1 order derivative of zeta k s first order derivative of ak s plus zeta k of s mth order derivative of aks. Now we'll substitute half in this equation. We have ak of half equal to 1. So we'll get minus zeta k m half equal to zeta k m half. And see, half is mth order 0. So the rest of the thing will be 0. So this zeta k m minus 1 half equal to zeta k m minus 2 half. These things are 0. So from this we can say that zeta k m half is 0. This is a contradiction because half is mth order 0. So order of half cannot be odd. What's that? Minus 1. Minus I have written there. M is odd, right? So minus 1 to the power m will be minus 1. Is it okay? So half is an even order 0 of zeta k. If zeta k of half is 0. So we know there exists a number field k such that zeta k of half is 0. Do we know there are infinitely many number field k such that zeta k of half is 0? Aramata-Brouwer theorem answer this question. let K over F be Galois extension of number field. Then zeta K of S over zeta F of S is entire. From this, we can construct infinite dimensional number field such that zeta K of half is 0. I'll erase this. This theorem is expected to be true for any extension of number field, that is a conjecture of Dedekind. Let K over F be extension of number fields. Then zeta K of S over zeta F of S is entire. And it is known to be true for number fields having solvable Galois closure. That's a theorem of Uchida and van der Waal. Let K over F be extension of number fields. And let K tilde be a Galois closure of K over F if Galois group of K tilde over F, here this is Galois. If this group is solvable, then zeta K of S over zeta F of S is entire. So Dedekind conjecture is true in this case. Let me erase this. So from Aramada-Brouwer theorem, we get that suppose we have a Galois extension and zeta F of S naught is 0, that implies zeta K of S naught is 0. So it's natural to ask, does the converse hold? That means suppose zeta K of S naught is 0, does that imply zeta F of S naught is 0? Okay, this is not true in general. This is a counter example. Let K over Q be Galois extension such that zeta K of half is 0. But we know that zeta of half is non-zero. So in general, this is not true, but this is true in some cases. In 1973, Heilbronn proved that let K over F be a Galois extension of number field such that degree of K over F is odd if S naught is a real simple zero of zeta k, that implies zeta f of S naught is zero. So this converse is true. This is true when S naught is real and simple zero. So next we can ask, is it true for higher order zero? So in a recent work with my advisor, Professor Sauli Gun, we have shown that let K over F be a Galois extension of number field such that degree of K over F is odd if S naught is real, odd order zero, that implies S naught is odd order zero of zeta f. So we'll get the following corollary. No, it need not to be seen. Just parity is preserved. Order is not seen. Okay, we'll answer this question. Let me finish that. So we'll have the following corollary. So let K over Q be a Galois extension such that degree of K is odd. Then zeta K doesn't have any non-trivial real zero of odd order. So for this kind of number field, if there exists a real zero, it will have even order. Earlier we have seen that is true for half. Okay, I'll stop here. Okay, yes, sir. It depends on the zero order of zero Artinel function. So if you can write zeta k as product of Artinel function, that will be Artinel function to the power chi of 1, right? So order of Artinel function times that chi of 1, that will show. So Yes, sir. Yes, sir. So that can be a bound for order of zeta k.
Like explicit examples of that theorem, or like how is that theorem proven, or
Uh, I didn't get your question.
right?
Existence.
Yeah, existence is there.
Explicit example.
Okay, I don't know that.
Expect that.
I'm not sure about that. Yeah. Uh, yeah, that is any zero. For this corollary, it has to be non-trivial zero. Here you are using the fact that Riemann zeta function doesn't have any non-trivial real zero, right? So this zero has to lie inside the critical strip. And this theorem, it is true for any zero.